In this lecture, we're going to begin going over statistics. So what are statistics? We have probability is associated with assessing the likelihood that an error event will occur. And statistics are used for design concept evaluation based because they provide a quantitative measure to things that behave in a random manner. So the best way to analyze an engineering problem is to conduct an experiment. When we take this approach, we face several questions of how many tests do we need, how confident are we in these results, can we extrapolate the results to other conditions, and can we estimate how the results lie within a specific range. So one way we can do that is to look at histograms. You can rate histograms by hand, and you can also, we're going to justify a reasonable bin size. So what do I mean? So this map shows the recorded earthquakes in a 7-day period. What do we want to do? Well, what are we going to do with bin size? So bin size is your x-axis. It's basically how many categories am I lumping things into. Based on my bin size, my data can look completely different. So these two graphs are showing the exact same thing, but with a bin size of 1 Richter scale unit per bin or 2, you get different types of data. So in the second graph, the fact that most of the earthquakes are magnitudes 2 or 3 get lost in the graph. If I do an even different bin, say I do 1 to 3, you're going to get another completely different graph. So it's all how are you wanting to represent your data. So how do you determine your bin size? To determine the number of bins, you take the square root of the total number of data points and round it to the nearest whole number. So if I have 940 recorded earthquakes, the square root of that is 30.66, so I need 31 bins. Then you also had to determine the range. The range is the maximum value minus the minimum value at a maximum of 6.7 and a minimum of 1. So to determine the number of items per bin, you take the range and you divide it by the number of bins, and then you round to the nearest whole-ish number. So my bin size is, in this case, 5.7 divided by 31, which is 0.02. 0.02, so 1 would be a good choice. Remember, the bin rules are given in the previous slide are suggestions. The actual bin size can vary based upon the message you are trying to convey. A Richter magnitude scale range from 1 to 10, so using 1 bin is the natural limit. Interesting, our bin size calculation was 0.2, and in each increase in 0.2 on the Richter scale corresponds to a doubling of the energy released. So to do another comparison of scale, if we do one based on a bin size of 1 or the bin size of 0.2 that we got, you can again see a completely different picture. So bin size really does become important. So then we're going to look at some statistical behavior. So we have to determine the mean, median, variance, and standard deviation of our data. We're going to justify our choice of using mean or median in estimating the central tendency of a data. And we're going to determine the relationship between variance and standard deviation. So what are mean and median? The average or mean is the estimate value representing of your population. It's the sum of all points divided by the total number of points. The median is the value between the lower half and the upper half. If you have an odd number of points, the median is the middle value. If you have an even, it's the average of the two at descending, and you have to put the points in ascending order. So what is the variance? The variance is how much are values scattered around the mean. So we're going to calculate that by doing the sum of the mean minus each point squared divided by the total number of points minus 1. So your original units are squared. So our variance is 1 divided by the total number of points minus 1 times our average minus 1 point squared plus the average minus the second point squared, all summed up. So what is standard deviation? Standard deviation is just simply the square root of your variance. You use it to restore your original units. So your standard deviation is just the square root of your variance. So next we have distributions. Let's look at some statistical distributions. We want to just draw the expected distribution given an expected change in the baseline. We want to assign possible causes for change, and we want to define what a normal distribution is. So distributions are used to show changes in data from your expected norm your expected values are your normal. A distribution is considered normal if the following holds true. These rules are known as the 68, 95, 9.77, 99.7 rule. Basically, it's the way your data lines up around your average. So a change in size of population is a change in the area under the curve and not distribution. So if I have less data or more data, a change in variance changes the spread of the data. So a smaller variance, it gets closer. A larger variance, it gets flattened. A shift in the mean will shift your curve left or right. So a range restriction, your data is cut off at some point, becomes non-symmetrical. Your distribution shape is going to drastically change, but the area is still the same. And then we have skewed graphs where if the mean or median are not similar, if your mean and your median are not similar, you're going to get an asymmetrical graph. So what about cumulative distribution functions? So what are CDFs? We're going to draw one by hand and using the following order: starting data and histogram data. So how do we create a cumulative distribution function for each bin? So we're going to sum the number of data points in and less than each bin, record the value as a percentage of the total points. So in our earthquake histogram in bin 1, we had 61 divided by 940 is 6.5%. So in bin 2, we have 61 plus 538, which is going to be 63%. In bin 3, we have 61 plus 508 plus 207, which is 85.7%. So what would that look like? Well, here's our original bin data, our cumulative percentage, as you can see in the line. Basically, you're showing how the histogram data relates to the percentage of your total data. That's it for this lecture. In the next one, we're going to look at statistical process control and doing statistics in Excel, so like how to make histograms and CDFs.